So in this tutorial we're going to look at the arrow theorem, so-called, but we're going to go through all the variations. And what you should see is that the idea or the picture of an arrow isn't a very reliable one for solving some of these problems. Anyhow, let's start by making a center here and drawing a circle. And then let's draw two radii. And the angle at the center here is going to be twice the angle drawn to the circumference if we're drawing the next lines that we draw from the same points. And a better way of saying that is that they share this arc here. So it's two angles that share the same arc. In other words, they come from both ends of the same arc. So what we can do is draw from the top here, actually draw this down and down to here. And that's your classic arrow theorem setup. And you should be able to spot it. You should recognize that this is the theorem that you're going to use is that the angle at the center is twice the angle at the circumference. Okay, so let's turn this into a problem. So here's the arc that they both share, and if we draw a line across from here to here and give ourselves, let's say that this angle here is 50 degrees. And they want us to find x. So how do we do that? Well, the angle at the center, let's call this ABC. The angle at the center, so that's angle AOC. Angle AOC is, according to the theorem, twice the angle at the circumference. So 2 times angle ABC. And you'd normally write it out in full, but I'm just going to do an arrow to symbolize the theorem that we're using, that the angle at the center is twice the angle at the circumference. So angle AOC, the angle at the center, is 2 times 50, which is 100 degrees. Let's just write that in with a different colour so we can see that this is our working, not what we were given. Okay, and to finish the problem, we can use the isosceles triangle theorem. In other words, the angle the two base angles of the isosceles triangle, here and here, must be equal. So 2x plus 100 degrees, it's got to add up to 180 degrees. And that's the sum of angles in a triangle. And I'm just going to keep that very brief. So 2x plus 100 equals 180. If we subtract 100 from both sides, we get 2x equals 180 minus 100, which is 80. So x, both of these angles at the bottom, x must equal 40. So there we go, and you might want to just notate in here as well that you use the isosceles triangle theorem. So isosceles triangle theorem, I'll just notate that very briefly, but it's best to write the reasons out in full, especially if you're in an exam and you want to get all the marks. Okay, so that's the basic sort of classic setup of an arrow theorem style problem. Let's now look at some variations. Okay, so let's mark a point at the center here, draw our circle, and draw two radii in exactly the same way. No, what I've done here is drawn a diameter. So the diameter is also 2 radii. So the radii here simply line up to form a diameter. But it's the same principle, so you have at the center here 180 degrees. So here you would have 180 degrees, okay? And that gives us what's known as Thales theorem, sometimes known as Thales theorem, or the angle in a semicircle. The angle in a semicircle, if we just draw any angle now to the circumference, must be half the angle at the center. So the angle at the circumference is half the angle at the center. The angle at the center is twice the angle at the circumference. So what does that mean? It means if we draw a triangle in a semicircle like this, the angle here will always be a right angle. So that's a kind of bonus theorem, if you like, circle theorem, that you get from the arrow theorem, and the idea of the angle at the center being twice the angle at the circumference. Okay, so that's one to note, very easy to spot, easy to learn. Let's do something a little bit more difficult. Now this time we are going to reproduce these radii here, but what we're going to do is this line that we had going upward here, we're going to actually bring it right down so it goes past the center, and in fact it will cut across this line here, so it cut across here. So when I draw this line, I'm going to draw it right across here. Okay, so it's still going to the circumference, we've still got the same idea, but it's going to the circumference and forming a very different shape. So something like this. Now, in this situation, we've got exactly the same idea. We've got an angle at the center and an angle at the circumference, and they're both subtended by the same arc. So if I draw the arc in here. However, it's more difficult to spot. People learn this arrow shape, they get used to that, and they get confused when they see something like this. So what we can do now is find x. Let's say x here. So let's just say that's the angle that we want to find, and let's say we're given an angle here. Let's say this is what could that be? 50 degrees again. So let's just say that's 50 degrees. And we might be given an angle here, but if we did, that would be a red herring. We don't need it because we've got enough information now to find x. So problem B, we've got the angle, let's just label it up first. So A, B, C as before, and the center O. So the angle AOC is again going to be equal to twice or double the angle at the circumference, which is angle ABC. Same reason. And we've got the angle at the circumference, so that's 2 times 50 again, which is 100 degrees. Now, slightly different finish to this problem though. We've got the angles on a straight line. So I just extended this line here. So we've got the angles on a straight line. So what I'm going to do is just put my working in so I can see the problem clearly. So we've shown that this must be 100 degrees because that's the angle in the center, twice the angle on the circumference. And now to finish the problem, we've got x must equal 180 degrees. Subtract our angle at the center, giving us 80 degrees as our answer. Okay, so a little more difficult to spot, But once you've got used to the idea, it's all about the two angles that share the same arc, that are subtended, we say, from the same arc, then you shouldn't be reliant on this arrow shape, and you should be able to see that this is exactly the same. You've got the angle at the center and the angle at the circumference. Okay, so now let's do one final problem. Let's just erase this. One final variation on this theme. So there we go. Now this time what I'm going to do is define an arc which is longer than we've seen before, and I'm going to make it go all the way around here, in fact. So now let's draw a radius like this, like this. But say that our angle at the center is all the way around here, so it's a reflex angle. It's greater than 180 degrees. So here's the arc, not this. And when you get a situation like that, then the two ends of the arc are going to be here. So we now need to draw to the circumference. Well, that's going to be to draw it up to here. So something like this, down to here. And again, we need to put in some values. So let's say again 0, A, B, C. And this time let's have this as x. And well, that looks to me like about 120, so let's call that 120. And this is problem C. So problem C, the angle at the center again is twice the angle at the circumference, but now we need to remember that because the arc, let's just indicate the arc, so the arc is all the way around here, because that's the same arc that these two angles share, then it's got to be this angle here. So let's just make that very clear. So it's this angle here, the reflex angle, not this angle here. So we can't say that x is twice this angle at the circumference. What we're saying is that this reflex angle here is twice the angle at the circumference. And if you think about it, that looks right, because that would mean this is 240. So let's say AOC again. There are different ways of notating that, but I'm just going to say the reflex angle to make that really clear. So it's this one here. So the reflex angle, AOC, is also twice the angle at the circumference. So angle ABC, which equals twice or double 2 times 120, which is 240 degrees. And to finish the problem, x then must equal 360 degrees, so the axiom that says it's the angle all the way round, minus 240, which gives us x equals 360 minus 240, which is 120 degrees. Okay. Okay, so now how do we prove the arrow theorem? Well, it comes from Euclid's Elements, 3rd to 4th century BC philosopher, book 3, proposition 20, and he's the one credited with discovering that in a circle, the angle at the centre is double the angle at the circumference when they share the same arc. And it's sharing the same arc that really gives us the clue about how to work out the proofs of these different variations on the same idea. So if we start with this idea of the two radii and draw then our arrow shape, then one thing we can do to work into this and get a proof is we can draw up these 2 points here to get 2 triangles. Now, in previous proofs we've looked at triangle congruence. Here, clearly, because this could be over to the left or over to the right, we're not going to get congruent triangles, but we are going to get enough information from making 2 triangles to be able to prove the theorem. So how does that work? Well, let's start by labeling up our diagram again. So A, B, C. And the very first thing that we can perhaps think about here is isosceles triangles. We've clearly got 2 isosceles triangles now because this line, and this line are all radii. So what I'm going to do is use a little bit of algebra just to make things clear. If I label this angle here x and this angle here y, okay, then we can say that this angle here must be x as well, and this angle here must be y. Okay, now what have we got in the centre here? Well, the angle here must be, and I'll write it here to be clear, 180 degrees minus these 2 x's. So minus 2x gives us this angle here. And this angle here, similarly, is going to be 180 degrees minus 2y. Now, finally, in this proof, and I'm not laying it out formally, but you can see how you would write it out in steps, you've then got the idea of these angles here. And these are angles on this straight line. So this must be 180 minus this angle here. So if I just do an arrow so you can see it very clearly, we've got 180 degrees minus 180 degrees minus 2x. So in other words, we can say 180 minus 2x. If I put that in brackets, then that's going to change to a plus. We're going to have 180 minus 180 plus 2x. The 180's cancel, giving us just 2x then in the centre there. Okay. Similarly, using the same algebra, we're going to have here the angle 2y. So now we've got enough information from our diagram to be able to prove the theorem. The angle at the centre, let's put the angle A, we haven't labelled it yet, so let's call this O, OC, okay, the angle at the centre here in our arrow theorem idea, our arrow theorem which says the angle at the centre is twice the angle at the circumference. Okay, so the angle at the centre is, well, now 2x plus 2y. 2x plus 2y. And the angle ABC, so the angle at the circumference, is, well, it's just x plus y. So x plus y. Therefore, we've proved the theorem that the angle at the centre equals 2 times the angle at the circumference. Which was to be shown. Okay, and maybe a way of making that just a little bit clearer is to rewrite this one by factoring out the 2 times x plus y. Okay, so finally we need to just add something if we want to provide a watertight proof for all cases. We've proved it for the arrow format, but what if, for example, we run a line along here and run it down here? Well, with the arrow theorem we needed to divide using this central line here into 2 triangles. Here we wouldn't need to do that, we just work with the single triangle. Let me erase this to make it clear. Okay, so in this situation where you've got more like a flag shape, you only need to work with this triangle here. So you've got an x here, and because again it must be an isosceles triangle, this must also equal x. So you've got 2 x's here, so this is again 180 minus x, giving us 180 minus 180 minus 2x. In other words, by the same reasoning, giving us 2x in the centre here. And this is quite important when we come to the more difficult case that we're going to work on now, of when the line here and the angle move below the centre and we get this sort of crossing over pattern. So when we've got something like this. Alright, now in this case we do need to draw a line again, but we're going to draw it not through a triangle to create 2 triangles, but we're going to draw it again from the angle at the circumference to the angle at the centre, like this, creating a new point here on the circumference that we're going to use for our proof. So if I call this point D, and again we'll have the centre here, and although they're not a triangle, we'll still label this A, B, C. Now the situation here, if I just indicate it in colour so you can see very clearly what's going on, is that we're going to, by the same reasoning, we've got this sort of flag shape here. So here are 2 angles, one at the centre and one at the circumference, made here and here. So this angle must be twice this angle. And we've got another arc, shared arc, which is just between D and A. So that defines this angle here as being twice this little angle here. And the reason why we need to do this is because to get at the 2 angles that we want to find for our proof, we're going to subtract the red from the green to give us this angle at the centre, the AOC angle, which we're going to prove is twice angle AOB. So it's we need to subtract the larger angle from the smaller angle to get the angle that we want to find. So a little trickier, but nevertheless the same sort of idea. So let's go ahead and prove it. So again, we need to start with the red angle, and so we're going to say angle DOC. DOC is twice the other red angle here, if you like, the other angle which is DBC. So angle DBC. And to make this proof easier, again using a little bit of algebra helps enormously. So I'm going to call this angle Z, so we'll call this a red angle Z. Let's mark it in red then so we can see it clearly. So the red angle we'll call Z. And by the same proof that we used before, this angle then must be 2Z. Okay, so completing our statement, we've got angle DOC is 2 times angle DBC. In other words, we're defining that as 2Z. Now for our second statement, we'll work on the smaller angle, the green one here. So angle DOA again using the same reasoning. So with the green angle we've got now this similar to the flag shape, so we've got a shared side here, so we know that angle DOA is also twice angle DBA. And let's call that y. So if we label that y, then this must be 2y using the proof that we worked on before. Okay, so angle DOA is 2 times angle DBA, and angle DBA is y, so 2y, we're defining it as 2y. Now let's go for our proof. Angle AOC, so let's put therefore, angle AOC has got to be, well, 2z minus 2y. Minus 2y. That's a bit wobbly. Let's make that a little clearer. Okay. 2z minus 2y. And the other angle at the circumference, so the angle at the circumference, which is angle ABC, you can see is just z minus y. So once again, might make it a little bit clearer if I just factor out the 2, so we've got 2 times z minus y, like that. Therefore, once again, angle at the centre is double the angle at the circumference.